I'm Lee Giles from Penn State University, and I might be the only professor here. Are there other professors in the room? So I didn't give there's nothing. I'm going to let you go look me up on the web if you want to find out something about me, because my homepage is there. And so what I'll be talking about today is using Solr Lucene to build CiteSeerX and Friends. And by friends, I mean other seers that we've built. And I'll give you some examples of those. So this is going to be a little bit different talk than you've seen before, because I'm going to talk a lot about things we built and how we're using Solr Lucene. And I'll give you some examples of those. So I just want to give you an idea. These are some of the seers we built. Some of these are online, and I'll talk more about that in a moment. By the way, if you see a seer online, it's usually ours. Porn seer is not. Okay, so that's not one we've built. So these are the people that we've worked that have worked with CiteSeer over the years. The current funding is NSF and Dow Chemical. I'll talk a little bit more about Dow Chemical, but we've had various past funding from NSF, Microsoft, Lockheed Martin, and others. So this is an outline, just briefly, give you a little motivation. And I'll talk about SeerSuite, and these are the tools that we use for creating the seers, and some of the specialized data that we use, and then how we use Solr Lucene, which, by the way, we are so grateful for. I mean, we're like unbelievable Solr Lucene fans. And then I'll talk about the disciplinary seers and some interesting things, especially about chemistry that you might like. And then briefly about the other seers, and then some opportunities for research and conclusions and directions. So I don't know if you've seen this new shift in the paradigm of science. Jim Gray and others have postulated that science now has become data-driven science, and that to have data-driven science, you're going to have all this data that you generate, that you create, and what's really crucial for this is search and access. So we see ourselves as fitting into this, fitting into giving access to scientists in terms of the type of data and documents that they like to process. So what I want to say up front is that our customers primarily are scientists and academicians and sometimes government. We also work with small science. Now, you might not know much about small science because you're probably more familiar with big science. Big science is astronomy, high-energy physics, things like this. Small science is chemistry. And chemistry has a lot of impact in terms of the field of science. But in chemistry, you keep your data close, and you don't share it so easily. But your data is exploding. So you want to also, so here you have to take the analysis to the data, which means the kind of work you're talking about here, Solr Lucene, building special search engines for the chemist, is very appropriate. So let me go to SeerSuite. SeerSuite is our open source search engine and digital library toolkit, which we developed based on Solr Lucene, that we've built these various seers with, and it supports research. And since I'm an academic, we like to do research. And it supports research in a lot of areas, from indexing and search to digital libraries, to data mining and structures, to information extraction, to social networks, scientometrics, informatics, systems engineering, software engineering, and web crawling. And I'll mention just a little bit about the web crawling, because we crawl the web. So we complement Solr Lucene with web crawlers. And also, by the way, train students, which some of you have been, in these tools, and these students we found are very popular both in industry, government, and academia. So let me just tell you a little bit about the SeerSuite properties. We try to make it modular, scalable, extensible. We try to have integrated features. The focus crawler that we use is Heritrix. I don't know if you know about Heritrix. It's a commercial-grade open-source crawler. It's the one used by the Internet Archive. Of course, we use, for the indexer, Solr Lucene. And then what we end up doing often is we end up building special purpose metadata extractors for populating the fields in Solr Lucene. And this has been our bread and butter, introducing these type of new metadata extractors. So it's all built on Linux, and our position is reuse, not reinvent. So we reuse a lot of, if there's a CRM, a conditional random field, a model out there, which we just talked about, which is what we use also, we use that. If not, we will build our own. Now, these are the Seer Friends. Now, they're in various stages of their life cycles, just like all of us. And so there are mature developing ones like CiteSeer, which is now CiteSeerX. There's ChemXSeer, Does anybody know why there's a subscript instead of a superscript for ChemXSeer? H2O? The chemists like this. And then TableSeer and USeer. And then there's some new ones, and some of these are public, and not all aspects are public, like ArchSeer, which still is up and running, Archaeology, which we hope to maybe working about up and ready soon. We'll put that in soon. I'll talk about it hopefully briefly at the end. CollabSeer, which is up and ready already. RefSeer, which you should try out, sort of neat. I'll talk a little bit about that. SeerSuite and GrantSeer, ones that we have working internally. And there's some dead ones, but there's one that just came, that was just revived. AckSeer now is up and running. It's the first acknowledgement indexing search engine available on the web. It has over 500,000 acknowledgements in it. And you can look at who's more acknowledged, mom or dad, NSF or DARPA. And there's even some interesting people acknowledgements in there. IBM or Google. And then BizSeer, which is gone, BotSeer is gone. And then we've proposed some others, and these come up in our proposals. And those don't exist yet. So why do we use Solr Lucene? I know everybody's here is here because you use Solr Lucene, but we really looked very strongly at competitors that we thought would be appropriate for what we do. And some of the competitors that we've looked at, Indri, Wampus, Terrier, are ones that come up immediately. But everything must scale with both the number of documents and the number of users. And we found Solr just beat everybody in that sense. I don't know if you've seen Watson, but Watson uses both Solr, Lucene, and it uses Indri. But remember, there's only one Watson. There's not many Watsons that use it. We find it's easily integrable and customizable, and we like the community. So let me just go straight to probably our most popular instantiation of SeerSuite, which is CiteSeer, now called CiteSeerX. So CiteSeerX it crawls the web for academic documents and ingests them, parses them, and then makes them available for you to search. Right now it has about 2 million documents, 40 million citation mentions, 2 to 5 million authors, 2 to 4 million hits a day, about 800,000 individual users, and we share the entire data set. We give everything away. So if you want to ask for it, we mostly do it over Amazon S3. The index is about 50 gigs. This is a screenshot of it. You can find it there, and you can see here our usage. Our usage has gone down in the U.S. Outside the U.S. has gradually increased, but we still have a large usage in the U.S. Oh, just a brief of the history. It was a project that we started at NEC Research Institute with these three guys. That's me when I was trying to look good for any prizes you wanted to give me. It was hosted at NEC from 1997 to 2004, and then we had all these features, which I'll briefly talk about, and then we refactored it and redesigned it to CiteSeerX, and that was released in 2008. And CiteSeer has been running continuously for 15 years. That's a long time for a search engine to be around. This is the architecture. It's as a web application, focused crawler with document conversion and extraction, document ingestion, document storage, then we have maintenance services and some federated services. And if you're interested in a discussion of this, you can look at our paper published in Usenix in 2010. We actually have 4 systems. And 4 systems, one is for production, one's for crawling. Crawling eats up a lot. If any of you do active crawling, you know that's a big resource and a big hog of storage. We also have a staging system, which we don't do very well. But most of our systems are research systems that the students do research on. And we've been talking about how you can cloudize these, and we've started to cloud some of them. And again, you can find another Usenix paper in 2010 if you're interested. So these are some of the services CiteSeerX now offers. It's very automated. We try to automate as much of it as we can. So we actually extract, using various techniques, the full OAI metadata. That's called the Open Archives Initiative metadata. We do the full text, and we have different indices for documents, citations, and tables, and we'll have different indices for algorithms, figures, and acknowledgements. The acknowledgements is already available, but we don't give that away just yet. There's a citation graph, which we construct for ranking based on citation. We do our own author disambiguation, not that we want to do that, but it's because we couldn't find algorithms which would scale the way that we would like them to scale. Remember, we have 4 to 5, I said before, we have 2 to 4 to 5, over 5 now, million author mentions. We want to uniquely cluster those. That's a power law. So we, and we also have to discern when that new person comes in. And so we built our own methods for doing this since we couldn't find others which were open source and could scale well. We do automatic crawling from a list and submissions, and then we do some personalization. Now the focus crawling is interesting because we're actively crawling the web. We're crawling right now for documents in the web. We had various crawling and scheduling algorithms for doing this. But one of our most interesting approaches recently was going to a whitelist and a blacklist. So, and looking at the trade-off between those. And the whitelist blacklist paper will be coming out in Web Science this year. This is just an example of the documents. I don't know if you can see this from the back. Whenever I give this talk at CMU, they really like this because CMU is number 1. And then right behind that's MIT, and these are the number of citations and the number of documents. And what's interesting is that we can get 90% of all citations from the first 550 sites and 90% of all documents from the next 1,200 sites. So how do we get metadata from these fields? This is the best way to get metadata, by the way. And it works really well. And if you can scale this up, it's trusted metadata. But to get trusted metadata is hard to do. So we do automatic, we extract and create a lot of data to make it into metadata. So the way we do that is we convert from PDF and PostScript to text using converters. First, we have a filter that sort of tells us that this document is a PDF, is an academic or scientific document. And actually, there are just some simple rules you can do for seeing if that's the case. And then we look for dupe. And by the way, duplication detection, as anyone will know, is still a research area. It's non-trivial. And we do have duplicates in our database. We right now use TET, but our system is so modular you can put in PDF box and others in there if you don't want to use TET. And then that's when we do the filter detection, and we do that with references and checksum. And then we use our tools, or you can build your own, to do various types of information extraction. Like we use an SVM, a support vector machine, for the header and parser, a conditional random field, and this is Parsit, a system we developed, which is open source you can download and use for extracting various entities from the document. And then we also use some various rule-based templates for extraction. And then so this is sort of the example of the automated database we create. And by the way, this has errors in it. But it's a very large database, and this is something we share on a regular basis, usually about once or twice a week. And you can see where it has, this ID is a number ID we came up with. It's not the real document ID that if you look for DI on the web. And then we look at titles, abstract, years, papers, publications. And then we try to do the version of it, and then we put it into a cluster. We put it into repository ID, a crawl date, sites in, sites out. And then if we can find the venue and the venue type, we put that in. Now, if you do CiteSeer search, the way we do this to enable search is you can do full text through Solr Lucene, and these are the fields we create with Solr Lucene. For instance, title, authors, citation, venue, keywords, abstract, range, citations. And some of these, by the way, we don't have, because the extraction process is automated, so it makes errors. So it's a noisy data set in a sense, but on the other hand, it's one of the largest metadata sets of citations and papers that you'll find. This is the field schema that we use, and these are the various fields that you'll find in Solr Lucene. And if you do the search results, you can sort based on relevance, which is the default setting, the citations, which is based on the citations received in the document and the collection, plus default. And that, by the way, we cut off at 500. If you got over 500, we say you're all the same. The publication year and the date of acquisition. You can go to CiteSeerX now and do this search. And there's a citation graph that's created. The query response, the queries at the interface with JSP. We hand over to the web with the application with Java Spring. It's response from the Solr JSON. And then the response is unwrapped and then put to, and we use our DB to help us do the query response. And then the response is presented at the interface using JSP in our system. Name disambiguation is a great area. In fact, it's still a research area. Those of you who do NER, name entity recognition, know that. You can go and the way to find this out is the best way to do name entity recognition is to use other information related to the name that you want to classify, like the affiliation for authors, maybe the keywords that you extract from the document, citations. Actually, citations is really good because most authors always cite themselves. So that's a very good way for doing name entity. So we developed some algorithms for doing this in CiteSeer. We make this public. In fact, we think we're one of the few academic document search engines which do name entity disambiguation and allow you to look at that. Let me go to chemistry. Chemistry is a very different field. Are there any chemists in here? Oh, no chemist. Chemistry is a very popular area. It's been around for a long time. The companies are very powerful. They have lots of money, and they have done research for a long time. It's recently been a very poor data field, but now data is exploding with them. The journals and societies are very sensitive to their IP. They have standards. In particular, there's CML, chemical markup language, and it's very much like computer science is sort of algorithmic centric. Chemistry is molecular centric. They don't really have much when it comes to algorithms usually. So we proposed this ChemXSeer architecture, which was to integrate well-used open source tools in chemistry, with CiteSeerX. So we looked at various things that chemists would like. And chemists had some really interesting requests. And I'll talk about these as I go through this. One is they like to search for chemical molecules, and they like to do molecular search. They also like to search tables and get data in tables. So we asked chemists, why are you interested in the data in tables? Well, you know how we get it now? We send the grad student to the library with their computer, and they put it in manually. So, the field, it's an old field, right? It has data from a long time, and that's in these tables is sometimes the only place you can find that data. So this is ChemXSeer. This is now funded by Dow Chemical. So let me give you an example of challenges in formula search. So this work was funded under nitrogen, iodine, hydrogen grants in Yellow Springs, Oxygen, Hydrogen, USA. Helium has published over. So you can see now we have some tokenization problems, right? These are simple. We've got to make our own tokenizers just for chemistry. So we've used machine learning methods, SVMs, and continual random fields to give very high accuracies for doing formula identification versus he, NIH, and Ohio. Okay, it's not, this is a long word, right? So this is one chemical formula. And by the way, I cut it off. It keeps going for a ways. So chemical formulas are very different from words. So there are different issues. There's parsing, there's extracting and tagging, there's indexing, and there's ranking. And I'm only considering one-dimensional formulas. Okay? One-dimensional. This is a one-dimensional formula, which in reality this is a 3- and sometimes 4-dimensional structure. So the tagging, you want to be able to extract the tag, extract the name of the chemical formula, or maybe even things like water or hydrogen peroxide, and tag those. Now you want to do indexing. Oh my gosh, what's your indexing scheme? What's your tokenization for indexing? This is a very interesting problem, and to our knowledge, unexplored until we looked at it. Now, there are indexing systems in chemistry, but they're not public. They're all private. So you can look at a frequency method. You can look at discrimination-based index schemes. And then these are the features. Should it be a formula, a partial formula? Something inside the formula? I mean, it's a lot of interesting things. And the only way you can know this is to know something about chemistry. Then you want to do the search. So now you want to do the matching on the things. How do you do that? That becomes quite interesting too. So we've proposed some methods for this, for exact formula search, frequency formula search, partial frequency search. And of course we do this all with chemists. Because if you don't work with the domain scientists, your work will not get used. So we work very closely with domain scientists to make sure this work suits the needs of chemists. And then of course there's a ranking function. This is just an example of the query models that we'll go into, because you also need to support different queries. Because the queries should be similar to what you want to do the ranking with. Now, so recently we've been going on to really graph search, three-dimensional graph search, and this is hard. This is a very hard problem. In particular, it's called substructure search, superstructure search, similarity search, and these are all NP problems. You know anything about computer science, these are just heuristics. So we're now just exploring these kind of methods. Table search. So tables are really neat because tables have a lot of interesting information in them. It's the only place they have that information. How much time do I have? 10 minutes, okay. So table search is really nice because the data there is very valuable. However, there was no standard table metadata representation. We had to create one for ourselves. And tables, what is a table? I mean, we actually had to go into the literature and find what was really defined as a scientific or a table, because there's a periodic table, right? There's all kinds of tables. So you had to really define what was a table. And now we've built these algorithms, which we call this first system CiteSeer. We like the term Seer. It's a branding term. And we use some box cutting algorithms to find the tables and pull the tables out. And then we parse the data in the tables, and we actually have the system up and running. It's not perfect. It's getting better. We've recently made it better. We have a paper coming out in AAAI on table header finding, which is an interesting concept in and of itself. You can do that, but to get a machine to do that is non-trivial. And this is the kind of metadata we generate. Now, this has been released and is open source. And we have table rank, which is the way whenever you extract something unique, you've got to rank it. And the ranking might not be the same as the ranking you would do, say, on the web or with text. And then this is right now in Solr Lucene, this is the things that go into our table index. I'm going to skip this. We're improving the extraction, though, under Dow Chemical support. We're also interested in automated data extraction from figures. So the chemists told us the way they got the data from figures was when the grad students went over with their computers, they also took a ruler. And they would measure the distance up on that plot, because that plot would be the only place you could locate that data. So we have developed, and this is ongoing work, developed methods for automatically pulling the table, like we pull the tables out of the PDF or PostScript, we can pull the figures out of PDF and then start processing it using our own little OCR. Obviously, this is a difficult problem, and we're only doing it with two-dimensional plots. We haven't gone to three-dimensional plots. So these are some of the things that we can do. We can extract the x-axis, the y-axis, the legend, and data points. Right now, we're hoping we might be able to do some extension to three-dimensional plots. I'll skip this. So this is CollabSeer. CollabSeer is an interesting project when we were trying to figure out how to do collaboration recommendations. So we have a huge collection of authors, right? And we know they're collaborators. So in this system, we recommend collaborators of collaborators. We can recommend dead people, but it just looks at who's been collaborating with who. And it works on about 500,000 authors, and right now you can find it there. And we had to define some special social network methods that would scale for doing this. It's built on SeerSuite. This is what it looks like, and you can go in and we give your ranked collaborators. A colleague gave us feedback and said, how can I really trust you to recommend collaborators or collaborators if you don't give me my current set of collaborators? So we show you these are the collaborators that you have right now. And based on your topic of interest, we will recommend different types of collaborators. And we show you who we're ranking, who we recommend. This is how Zhu should consider collaborating with Lee and vice versa. And this is the architecture that we use. And again, this is all based on Solr Lucene and the databases we've built with CiteSeerX. And we do this is the first time in this case we're doing a ranking method in some ways based on the social network and the textual similarity of the papers you've published. And so this, and the reason we use exponential is if it's a 0, in other words, we don't have any structural information about you, we just go to the text information and vice versa. Now this is an interesting system. This system is receiving more attention these days. This is RefSeer. And RefSeer actually, you put your paper in and we recommend the citations you should use. This system is, there's one online that's competing with us right now at Ohio State, but we think this one's a lot better because it uses a lot more of the context. The one at Ohio State doesn't use as much context. So this is an online system, again, built on CiteSeerX data and Solr Lucene. By the way, you can do various issues. You can really change things a lot when you want to do a citation recommendation. Do you want something more contemporary? Or do you want something more older? Do you want something that's venue related, right? I mean, there's certain venues you might want to include in your citation. This is what it looks like right now. We've published quite a few papers on this. They're listed above. And these are some of the papers we recommend in the citation you would do if you put in this abstract. We've also done some work with expert search. And because we have this large data set, which we share, you too can build an expert search system based on the data that we've collected. And this is when we look at machine learning, these are the people that we come up in our expert search system. And we also give you a link. You can't see this from back there, but these are the various fields that we think are appropriate for defining this expert. Now, this is something we've not really made public, but I just thought I'd bring it up. It's GrantSeer. So this is a prototype system for people who want to manage grants. And we did this in work with NSF, who were interested in how they could do their better management of their portfolios of grants. And the idea here is you link the PIs with their grants, their publications, their citations, their organization, their expertise, and the data that can be shared, like from Google Scholar or CiteSeerX. And then, you would have something where you'd put in a university, and it would list all the people up there, their grants, and these would be the word cloud of what's been associated with these grants. And this is a working system we use internally for evaluation and also to show others and maybe to get some more support for. But the nice thing about this, that the take-home message we like to give is that you can build these things pretty quickly. Solr Lucene if you got the data, Solr Lucene really helps you do demos and build things up pretty fast, we think. It took us about 3 or 4 weeks to build this. Okay, this is AlgorithmSeer. Now, what really costs you time is extracting the data that you want to use in your indexing and in your fields, in your ranking. So here what we want to do is extract algorithms and mentions of algorithms in papers. And this is starting to work. We hopefully will have something up and available soon. We have it internally. And what we do is we go in and we try to find also pseudocode and extract pseudocode. And we're doing analysis of pseudocode. So we want to be able to recommend papers to you that have certain algorithms in them. So if you're looking for certain types of algorithms. And the metadata extraction, we extract pseudocode, captions, reference sentences, right, when people talk about the code, and a synopsis, and then we use this with the Solr. This is AckSeer. I'm running out of time, I think. How much time do I have? 10 minutes. Okay, so this is AckSeer. So AckSeer is an acknowledgement search engine. You can search for, it's online right now, ackseer.ist.psu.edu. This allows you to do searching on who's well acknowledged in various papers, and in particular, if you want to do the top acknowledged entities in terms of citations and acknowledgements, you can see National Science Foundation. And then, by the way, all these were created using open source NER tools, which we've actually cleaned up a little bit. If you go further down, you'll find that there's some things that occur there that are not really organizations. So even current state-of-the-art NERs do make mistakes. For example, if you look for individuals, John Wiley comes up as an individual. And so does Carnegie Mellon. Well, they are people, right? I mean, they were people at one time. But these entity systems do make some errors. So let me just summarize. We propose an infrastructure for academic, science, and search engine digital library creation. We've made it pretty modular, scalable, and extensible. It's pretty robust. It's built on open source, robust tools. It's easy to apply to various domains. In particular, we do something that's maybe not the standard, but we build separate indexes and then combine them in sort of a universal search, which also is a nice research topic. But what this allows us to do is by building separate indexes, you can break the projects into digestible components that students can go after and do, and you can put them together, and if one fails, well, that's okay. I mean, the rest of the system's still working. So it's a nice way of doing research that not everybody does. But if you want to see what universal search does, go to Google and they'll put in the universal. I mean, when you do the standard query, that's universal search. So this also, because of the system, you can do research. You can do research in data mining and information extraction for real systems. And these systems, the way we built this system is you can easily put in these extraction plugins. So now you can focus on scalable information extraction methods. And you can also use this to automatically populate databases or data structures. And we've demonstrated this with beta systems in quite a few areas. The systems are pretty easy to build. The issues really are data collection and data access. And then, of course, you have to face the extraction, the indexing, and the ranking issues that often occur. And there are many ways to use this as a research testbed. It's used for a research testbed for others who want to do similar research or just check out how well their systems work on an established data set. And if you want to find any of these seers, usually just go to Google, put in the names, or go to my homepage. So I think there are a lot of opportunities here, and I would like to encourage more people to move more towards, government, academia, and science, because there's a lot of opportunities there that people have huge amounts of data and they really are having problems indexing and processing and giving access to it. It's a gold mine. The problem is there's not as much money in it. On the other hand, there's a lot of opportunity, I think, to take advantage of what you extract and you do with maybe other issues like startups. And by the way, the digital humanities is not far behind, and we're going to see a lot of search tools for the digital humanities. And their needs in large-scale data management, usually from tera to peta. I mean, our definition of large data is if you can put it on a laptop, it's not large data. But large-scale data mining, information extraction, it's important to use domain expertise. You want to work with domain experts to make sure that the systems you build are very appropriate. Reuse, not invent. And Solr Lucene is a great tool. I mean, we could not do our research without Solr Lucene, and we use it all the time, and our students are well trained in it. So human attention is a scarce resource, not information. So thank you for your attention. I think that's, I'll end there.
On the citations, do you compute a citation graph, or is it a one level forward backward citation?
When we do the citation graph, the question was about the citation graph. The citation graph goes to all the things it's, the papers, but it doesn't go any further. It stops, right, if that paper is not in our database. So, right, I mean, we can't go any further than the paper in the database unless somehow we could get the metadata for that paper and its citations.
So if a backward citation happens to that paper later on, say a paper is published today, and 1 month down the road, 6 of them cited, and 2 months down the road, 12 of them cited, do you actually go back and update the index of the paper? Or?
Oh yeah. I mean, whenever we get a new paper in, we extract the citations and then update the citation graph, right? So, and if that paper has been cited, we look to see if that paper is cited someplace, right? So it's a database of citations and cited, and then we just fill that in and look for that every time we parse the document. Now, maybe this is what you're asking: how good is our parser for doing that? As far as we can tell, it's one of the better ones out there. We would use anybody else's if there were better ones that were scalable. But ours parse it. It's open source. You can use it. Thank you very much.